Hello students, in this class we will discuss about laser modulation in general, and I will elaborate on what is Q switching and mode locking. Quickly we will go to the basics of laser a little bit, and with that review we can straight away discuss about the modulation. Laser, as most of us know, it is light amplification by stimulated emission of radiation. The basic principle on which this phenomena occurs is absorption emission principle. When a photon of light is incident on a proper medium, which is a laser medium, these three processes can take place. Which are this? There can be absorption. An atom can go from the ground level to the excited level, and from there it can spontaneously come down to the ground level, which is known as spontaneous emission. But if there is a possibility of having a stimulated emission, then lasing is possible. Stimulated emission means, as most of us know, we force the atoms in excited level to go to an intermediate level known as metastable level. From there, by a trigger photon, which may be due to spontaneous emission, lasing action starts and you get a laser out of that medium. So what are the basic things that we are supposed to have for the laser action is there should be population inversion. That is, the number of atoms in the excited level should be greater than the number of atoms in the ground level. In order to achieve this population inversion, we are supposed to have a metastable state. So these are the components. We have to have an active medium. Not all substances or the compounds can give us laser. Only a certain medium can give us laser. It should be such that spectrally there should be a possibility of having 3-level or 4-level excitation. The next component is pumping system. We should have a proper pumping system which will be the source of the photon which can be put into the active medium. The pumping system can be optical systems such as xenon in case of ruby laser, or it can be electrical, or it can be a chemical reaction too. The third one is quite important, which is resonance cavity. It's a very simple arrangement of a pair of plane mirrors arranged, in between which the active medium can be placed. One of the plane mirror is 100% reflective. The other plane mirror is partially reflective, through which laser comes out. Therefore, that is called as exit mirror or output mirror. The laser which we get has a special property. Laser light is highly coherent. It has great directionality, very intense, and it has single wavelength, monochromacity. So when we get the laser output, out of the medium. In certain cases, we get a continuous wave. For an example, helium neon laser gives us a continuous wave of laser. But in certain other cases, we get pulsed laser. Example for that is ruby laser. You get a pulse of laser, then there is a gap, again a pulse of laser, and that continues like that. So when we come to the application of laser, for a particular purpose, we need to have the particular intensity or power of the laser, or we may have to have it for a very short duration. So when these kinds of need arise, then laser should be modulated such that we get a desirable output which we want. And process of doing this is known as laser modulation or laser tuning. There are various methods of doing this. One is cavity pumping, the other one Q switching, and the third one mode locking. And in this class we will focus on mode locking and Q switching only. What do you mean by mode locking? See, we know the essential component of a lasing system is a resonant cavity. A resonant cavity is basically an oscillator. So you have the stimulated radiations in the form of waves, and as the lasing action takes place, all the waves will not have the same phase. It means there are several pulses within the resonance cavity, all with different phases. In mode locking, what we do is we induce a constant phase relationship between all of these modes. Now, the laser which you get out of this mode locking technique is extremely short, the order of picoseconds or femtoseconds, and such a laser is very helpful in studying certain processes which are very quick. For example, photosynthesis, which is a biological phenomena of preparation of food using the light, which is a photon. It's very quick process. And breaking of bonds in chemical reactions. These things are very quick reactions. So we need lasers which has extremely short duration in order to study these processes. So as I told you, we are going to induce a constant phase relationship between different modes and let that phase be delta. So in the picture I have put two things over here. See, these are the different modes, and this mode has certain lambda and amplitude and therefore some frequency. And now this has a different one. So all the four shown here has different phases. If we can relate the phases of all the four and see that a constant phase relationship is maintained, then we are successful in locking the modes of all these waves. When the mode is locked, then we get a resultant pulse over here that repeats. So here, see here, all of them have the same phase delta, and therefore we get a resultant pulse. This is of extremely short duration. A bit of theory about this. See, we consider amplitude A naught of n modes, and then the frequency omega n and the phase delta n. When all these modes are in the same resonance cavity, the resultant is that they all combine linearly to give one resultant pulse, which is mode locked pulse, which we need. Therefore, it's a lead-end combination. Therefore, I have shown sigma from n is equal to 0 to n. This is the number of modes over there. And so when we consider the frequency of a particular pulse over there, all the other pulses will be having different frequencies. Let the difference be delta omega. So you observe here delta omega is equal to C pi divided by L. Therefore, in mode locking, the cavity parameter L is very important. L is the length of the gain medium or active medium. So that is very, very important. So we are going to force a particular phase delta n is equal to delta. So mode locking is done. And when we do that linear combination with all the interference over there, we get the equation, and the time interval for this mode locking T is equal to 2L by C. So at this time interval, the pulse laser, which is mode locked laser, will come out. When it comes out, it will have high intensity. Therefore, we see the equation written there for the radiance. So irradiance is equal to n square A naught square. Okay. Now, here one important thing we should realize is that our aim is to get a very short duration pulse. For this, we should have a large number of modes in the cavity. So that we can understand by looking at this relation 1 over n into 2L by C. Okay, so n becomes greater, the time becomes very, very short. Okay, right. Next, in this mode locking, we have two types. One is active mode locking, the other one is passive mode locking. In active mode locking, the inducing of phase relation between several oscillations is done in longitudinal mode, that is along the axis of the gain medium or the resonant cavity. So here we can vary the loss in the laser cavity at a frequency equal to their intermode separation, and that is equal to C by 2L. So what does this mean? It means when you place a shutter in between the active medium and the output mirror, I will show in the following slides pictorially, you will understand it better. What we are trying to do is, we are trying to stop the resonance by putting some shutter in between the active medium and the output mirror, so that the feedback cannot be got, and we open this shutter every 2L by C seconds. This keeps on repeating. Therefore, it's a very short duration. 1 by n into 2L by C is a very short duration for which the shutter is open and then it gets closed. Therefore, there is a periodic oscillation of the shutter which induces the phase relationship. So when as soon as the shutter is open, all the waves over there which interfere or which get locked over there effectively is not affected by the shutter. But the waves which comes before opening and after closing of the shutter, they are all clipped. That's how we control the phase and we induce the phase. And there are various shutters which are available. The most common ones are electro-optical shutter or acousto-optical shutter. Now they work on the principle of the focal effect or Kerr effect, and that we'll see what happens then. So using these shutters, the resonance cavity, the oscillations can be closed or can be opened. In other words, when you close the shutter, we are in the process of locking the modes. When you open, all the mode locked, that resultant pulse will come out very quickly. In electro optical modulator, we use a focal cell. In this cell, we just switch on the cell, apply some electric field. In the cell there is a crystal. This crystal becomes birefringent. Therefore, it is going to rotate the plane of polarization of the incoming light in to and fro transit of the pulse. Thus, it will close when you apply a field to the focal cell. The shutter is closed. Once there is no field, the shutter is open. Then all the mode locked resultant pulse comes out quickly. The other modulator is acousto-optical modulator, wherein we use piezoelectric transducer. So here we are going to produce a grating type of arrangement by piezoelectric effect in that medium, and then that can be used to shut or open the shutter, in which inducing of phase to lock the mode can be done. The next type of passive mode locking. In this passive mode locking, we will not place an acousto-optic modulator or electro-optic modulator. There, an operator should take care of that, switching on, switching off the modulator. But another passive way we can mode lock, which is known as passive mode locking. Here what happens is, we put a saturable absorber in the cavity. Now, what is the speciality of this saturable absorber? It is an absorber which can absorb light depending on the intensity, and the absorption coefficient is non-linear. So when such an absorber is kept in between the active medium and the exit mirror, if the light which is very low in power, the weaker modes it will absorb. For example, dye is a very good saturable absorber, although it has a disadvantage that it's quite toxic. So when a mode locked high power peak pulse hits this saturable absorber, it becomes transparent. We say the dye is bleached. It allows the pulse to complete the to and fro transit and finish the fluctuation and come out as a powerful laser pulse. All the other weaker modes die out, and they are all absorbed by the absorber. Okay. Now in this slide, and I have explained to you how in electro-optic modulator, where we use birefringent crystal, for an example potassium dihydrogen phosphate crystal, how it rotates the plane of polarization, thus it acts as an effective shutter. Now this is a schematic arrangement of the laser modulation. Look here, this is a high reflecting mirror, this is a low reflecting mirror, or this is also called as N coupler. You have an active medium, and all I have explained to you, the saturable absorber. According to the need, we can use many of them like this, as it is shown here. Saturable absorber, when you put, we are going to have passive mode locking, and for active mode locking, electro-optic modulator can be used. That's how we make it passive or active in nature. Okay. Now this is a simple representation of acoustic optic modulator. See, there is a transducer and piezoelectric effect takes place. Okay, the light which enters over here, there is a split, there is the diffracted beam and the transmitted beam, and because we are diffracting or scattering some of the beams like this, the quality or the Q factor of the laser cavity can be controlled. The next modulation method is phase switching. Phase switching is also called as uh, a method by which giant pulse formation can be formed. So here extremely high power single pulse can be obtained. It is having such a high power when compared to the continuous wave mode or the mode locking method. This Q switching is always preferred. So Q switching is also known as single pulse method. You have a very high energy of the pulse. Its repetitive rate is very lesser. It means you get a very strong pulse, and after a very long duration only you can get another pulse. Okay, so long pulse durations. When we compare this to the pulse given out by mode locking technique, there we have a train of pulses and that repeats quite often when compared to Q switching method. So in Q switching we have to say something about the quality factor of the cavity, Q. So this Q is what is switched. Look here, Q is equal to 2 pi into energy stored in the cavity divided by energy loss per optical cycle. Per optical cycle means to and fro transit, or it is also called as one round trip. So in one round trip, how much of energy is lost? The energy loss, as we know, is due to the reflectivity of the mirrors and scattering and all the other possible phenomena wherein the energy is lost. Okay. Now when we see here, if energy is lost more, that is going to control this Q. So when we control Q, through which we can also control the threshold condition. Okay. So in threshold condition we have to have the gain such that it is greater than all types of losses put together. Now in this representation we can very clearly explain what is meant by Q switching. In Q switching, see, there is a high reflecting mirror, this is a end exit mirror, you have a modulator over there. When we close the modulator, the loss is increased over there. Therefore when there is a high loss, Q is low. So at the same time what we do is we use a strong pump and pump the photon energy into the active medium. Therefore all these excited atoms, they occupy the upper level and they stay there. It means the gain is increasing. We are not letting them to come down. So when you keep on doing this, there is a very high energy which is stored over there. Then what we do is we Q switch it. Means I will show you in the diagram. In this diagram, see, this shutter is open The shutter can be some rotating mirror, okay. So when it is open, what happened? Q is switched. The loss goes to a very low value, and therefore Q value is great, and at that junction all this energy which is stored in the active medium is opened up. It is able to go the round trip and then come out as a very strong laser pulse. Okay, so when this happens, we say the cavity is depleted. Okay, and in Q switching also we can use passive technique or active technique. So this is how a Q switched laser works. So now let us see how it evolves, the laser pulse. See, at the initial stage, when the shutter is closed, loss is very high. During this time, pumping is going on and the gain is growing. And then you open the shutter, the loss drops to a very low value, Q has increased, and therein the laser output pulse starts building up, and there results a Q switched high energy pulse. In active Q switching, this is what happens. Loss is maximum, the shutter is closed. Due to pumping, the gain is growing and gain saturates. When the shutter is open, round trip is completed, and thus a Q switched pulse, high energy pulse, comes out through the end coupler. Alright, so these two techniques are very, very important, and it finds applications in many, many fields. So we come to the end of this session. Thank you. So it's always nice learning this beautiful phenomena of laser, the physics of the phenomena. Thank you.